Okay, so if you read the announcements, you saw I made a video. I didn't show you the video because at the very end of the video, because of a silly mistake I made, it was, well, worthless. The silly mistake was along the lines of, and I'm not kidding, I think on one line, um, there was a 3x, and I multiplied it by 2. And of course, as we all know, 3 times 2 is 4. Well, that's what I wrote down. Thus, a cascading effect all the way through my work, and it was just it had to be redone. However, it gave me an idea to do something better. So I'm going to start out, and I'm going to illustrate a point that the author of the book is getting towards. It has to do with the associated homogeneous system. But at any rate, consider this. There's a system of equations. We know what it is. It's one equation and two unknowns. But I want to solve it in the regular way that we've been doing it. So let's do Gaussian elimination. Well, it's done. So what's the free variable? Free variable is y. So we'll say y equals y. One way to write it as an ordered pair would be, well, the y coordinate is y. What's the x coordinate from here? You get x equals what? 1 minus y. So far, so good. We said we're not going to write it this way, or we can write it this way, but we want to go one step further and write it as the sum of a particular solution and a linear combination of the free variables. So how do we do that? What's the free variable? Y. What's the particular solution? Well, I can't think of an easier one. Maybe you can, I don't know. But if you set y equals 0 and you get x equals 1, you get this particular solution, x equals 1 and y equals 0. Remember, 0, I'm choosing that arbitrarily, right? By the way, I'm leaving this up here because we're going to do this problem after what I'm doing here. What's the free variable? Y. And we just have to think about, what does it have to be? Well, y is y, so we need a 1 down here. And what is x supposed to be? It's supposed to be 1 minus y, so we'll put a minus 1 right here. You see, when you multiply that out and add it to that, we get what we're supposed to get. Okay, now, what the book asks you to do in several of the questions is to solve the associated homogeneous system. What is the homogeneous system? It's where you set the right-hand side, the coefficients, equal to 0. So let's go back to the very beginning. There was the beginning problem, and here's the homogeneous system. We just set that equal to 0. First question you should have is, why am I doing it? It just seems like I just made up a new problem. Well, I did make up a new problem, but let me solve it anyways. What's the free variable on this system? Well, we're already solved. It's already, in echelon form. So say y is the free variable, so y equals y. Given that y equals y, x equals negative y. So we can write it like this. Y is y, x is negative y. That would be the kind of way we're familiar with. I want to write it this new way, a particular solution plus some combination, or in this case it's a scalar multiple, because we only have one free variable. If we have more than one free variable, then you might have a genuine linear combination. Scalar multiples times the free variables, and then they may be added together. But at any rate, what do we have here? What's a particular solution? Well, let's make y 0, and that makes x 0. So we have 0, 0, plus, and then let's see what we have here. Y, we definitely need a 1. What do we need there? Negative 1. Huh. Now compare these two, because you should be wondering, why would we do this? Or is there a relationship between the homogeneous system and the original problem? And I think here maybe you can guess at it. Let's see if we can make a graph of what's going on here. If I just graph this is the homogeneous system right here. That's the homogeneous system. I just rewrote it from up there. What does a graph of this look like? X equals negative y. Well, let's write it in a more familiar style. And the more familiar style would be to solve for y. So y equals negative x. And that's, I guess we're familiar with that. It's a straight line, slope of negative 1, crosses the origin, sometimes at an angle of 45 degrees with respect to the x-axis. Okay, now, what about this over here? I'm sorry, not this. That's this right here. What about this? If we want to graph this, what on earth does this look like? This system right here. Well, I think I had it written down a minute ago, but apparently I don't have it written down anymore. We had a 1 there. And that would mean y is equal to 1 minus x. And what does that look like? The y-intercept is 1. But what I want to say is it's the same line. It's the same line, and we just shifted it a bit. Now, what's going on here with these two solutions is this portion here is the same. These two are different. And hopefully now in your mind, you're conjecturing something, or you're thinking something, or making some sort of observation. You make an observation, and then you make a conjecture. What's the observation? These two are the same, these are different. What's the conjecture? Is it really, this determines the line, and this determines where you place the line, within this two-dimensional space. So again, this will tell you what the line looks like. In a way, this is the line. This tells you where to put it on that system. And now I want to try a three-dimensional version of this. So let's do a three-dimensional version of this. So allow me to erase this. And we'll make a three-dimensional example. Now, the graph in 3 dimensions is not going to be as easy. And one thing I said in the video that you're not going to see because of the silly mistake that I made that got me kind of riled up is the following. Go online. See what you can find in terms of graphing that'll make free and easy graphs of what we want to do, in particular, planes in three-dimensional space. So what we will want to have, because it's not easy to do by hand. We can do it, we can try. But if you had something like this, for example, here, I'm waiting for this to dry a little bit up here. But if you had something like this, let's say x plus y plus z equals 1. Something that will make a nice graph of that we can see. And even more importantly, if we want to graph a second one and see where they intersect. Because graphing multiple planes and trying to see where they intersect is pretty tough. It's pretty tough to draw. It's pretty tough to think about it. But it could be handy to have something that would do that. So here's one equation, 3 unknowns. I want to add another equation here. Let's say we had 2x minus 3y plus 4z equals negative 1. And that's our system. This is an example I'm just making up right now. We have two equations and 3 unknowns. Each one of these represents a plane. So what we know because of our geometrical insight is these are going to intersect in a straight line. But put that insight aside and let's go ahead and use Gaussian elimination to solve the system and then write it in this new way of writing it. And then we want to solve the associated homogeneous equation. And we'll see if our conjecture holds true, the conjecture that we just made. Okay. So what would I do first? I'll leave the first equation alone. We'll leave this first one alone. So x plus y plus z equals 1. We'll take this equation and we'll subtract twice this equation. So the x's will be gone. If I take negative 3y and I subtract 2y, we should have negative 5y. And then 4z minus 5z is minus z, and negative 1 might. I don't want to make, this is the kind of silly mistake that I made that I didn't show you last time. So I said take this and subtract 2 of that. So negative 3y minus 2y, that's negative 5y. 4z minus 2z is 2z. Now, look at that mistake I just made. It couldn't be more classic. I can see psychologically why I did it, because I had 5 on the brain. Nonetheless, 4 minus 2, so this should be a plus 2z. And then negative 1 minus 2 is negative 3. Now I want to step back because I'm having that kind of day apparently with the microphone issue, which I figured out too late, but I figured it out now. And I won't even bore you with the details, but let's see, this minus twice that, so the x is gone. This minus twice that is that. This minus twice that is that. And this minus twice that is that. Here we have echelon form. The free variable is z. So just to sort of emphasize that, I might write z equals z. Let's see, from this equation right here, let's solve for y. If I solve this for y, we would have, well, what I tend to do, and you don't have to do this way, but I tend to add 5y. I tend to get the negative 5y over on this side, I switch sides. So we have 5y equals 2z plus 3, and we get y is equal to 2 fifths z plus 3 fifths. Now, this is where I'm thinking to myself, wow, maybe I could have chose a better example so we didn't have to deal with fractions, but we're not afraid of fractions, are we? And let's go back up to the very top equation and see what we get from that. The very top one, if I solve for x equals 1 minus y minus z. So x equals 1 minus 2 fifths z minus 3 fifths, because that's y, and then minus z. So x is equal to, let's see, 1, and then negative 2 fifths z minus z, that's negative 7 fifths z. And look at, I almost made another careless mistake. 1 minus 3 fifths is 2 fifths. So this should be 2 fifths, like that. So let me write it in the standard ordered triple style. We would have x is this 2 fifths minus 7 fifths z. So 2 fifths minus 7 fifths z. That's x. Y is 2 fifths z. 2 fifths z plus 3 fifths. And z is z. Now, that's okay to write it that way. I mean, I know what it means. You know what it means. Everybody knows what it means. The slightly, I suppose, more official way of writing it would be to use set builder notation. And we would write it like this. I'm just going to copy all this. Such that, remember that vertical bar means such that z is an element of the real numbers. Okay, now let's write it with the new style. And then what am I calling the new style? I'm calling the new style where we write it as a sum of a particular solution and a linear combination. Well, what's a particular solution? I mean, again, if anybody asks me to pick a number, I'm almost always going to pick 0. If they don't like 0, I'll pick 1. If they don't like 1, I don't know, maybe I'll pick 2 or something. But 0 seems to be like a good go-to example. You don't have to. You don't have to. So oftentimes the author does and doesn't talk about it. And you might wonder, well, where'd that come from? And that could just be choose a number. You have to choose a number. I don't know, choose 0. It's easy. So if I set z equal to 0, what does that give me for the rest of this right here? I just noticed I'm missing a parentheses. I don't want to lead to confusion there. If I set z equal to 0, what will we get? Well, z will be 0. What will x be? 2 fifths. And what will y be? If z is 0, 3 fifths. Okay, so there's a there's a specific solution, and now I feel like choosing a different one. I'm going to stick with this one. Notice if I had made z 5, then we wouldn't have any fractions. Maybe we'd like that better. I don't know, but let's leave it like this. Now, how are we going to write this? We're going to write this as the textbook does. There's x, there's y, there's z plus some vector times z. There's our free variable. Now, what should it be? Well, z is z, so we need a 1 down there. What do we need in the other two spots? Well, let's see. What is x in general? Well, x in general is 2 fifths minus 7 fifths of z. There's our 2 fifths. So here's minus 7 fifths. And we need 2 fifths z plus 3 fifths here. There's our 3 fifths. We need 2 fifths. So put 2 fifths there. So this is the way of writing the solution to the original system as a sum of a particular solution and a linear combination of the free variables. Now, as some of the problems in the textbook ask you to do is now go back and solve the associated homogeneous equation. So let's do that. Now, if our conjecture is right, we should know what the answer is already. Okay, I'm gonna need this. I don't want to erase that. Let me erase all this here. Yeah, let's go back to the original. I don't want to take any chances after the ridiculousness that I just caused myself an hour or so ago. We're going to solve the associated homogeneous equation. So let's go ahead and do that. So we're going to make those zeros. Let's go ahead and do it like this. 0 and 0. We'll leave the first equation alone, like we always do. This one will subtract twice that. So no more x's. This minus 2. This is ridiculous. Why am I doing this? I'm thinking, did I do that right a moment ago? Pretty sure I did. Hope. At any rate, that minus that, negative 5y. And then this, oh yeah, remember that? Minus 2z, so we would get plus 2z equals 0. Notice the zeros are not going to change. When we do Gaussian elimination, it's never going to change the zeros on the right-hand side. So when we start writing this like matrices, we'll leave off, we won't even use the augmented matrix. We can just leave off the zeros. But for right now, we get this. Now we have a free variable, right? So z is equal to, z is equal to z. What about the rest of them? Let's take a look at this one right here. So y is equal to what? Maybe you get the 5y over there and then divide by 5. So 2/5 z. And what about x? What do we get? X is equal to negative y minus z. So x is equal to negative this. Well, what would that be? Negative 2/5 z minus z. So negative 7/5. Negative 7/5 z. Now this can seem strange. Oh, let me write this as an ordered triple. So as an ordered triple, what do we have? X is negative 7/5 z. What is y? 2/5 z, and z is z. So there we're writing as an ordered triple. But how do we write it in this style right here? Well, we need a specific solution. Okay, like z0. Well, 0, 0, 0. So you get this rather silly looking vector, but nonetheless it's the 0 vector. Of course, it corresponds to the origin. And Frank, you don't have to write it there because this plus or minus anything, any linear combination involving this will be 0. I mean, it'll be what the linear combination is. If you add things to this, it'll be that, right? Because it also acts as an identity, just like 0 does in regular arithmetic. So what do we get left here? We get plus, well, something times z. Well, z's got to be z, so that's 1. What does y have to be? 2/5. And what does x have to be? Negative 7/5. Well, lo and behold, this is the same as that. Now, it turns out that this conjecture is correct, that the associated homogeneous system will always determine the subspace. Now, I think I have to explain that a little bit. Think about 2 dimensions. We're not going to need this anymore. Think about 2 dimensions, 2-dimensional space, x, y, z coordinate system. In terms of terminology, we can refer to that as a space. We can refer to it as a lot of different things. It's often called Euclidean space or Euclidean 2 space to mean 2 dimensions. We may call it the XY coordinate system, a rectangular coordinate system. Okay, so it gets called a lot of different things. Symbolically, it's often written like that. Remember, that's a symbol for the real numbers. Think about an XY coordinate system. You have an x-axis and a y-axis. What you have is the real numbers, and this is the way we talk about it, crossed with the real numbers. Or the real numbers times the real numbers. I mean, it's not multiplication in the normal sense, but we can refer to it that way, and that's where this terminology came from. And we'll do 3D in just a second. We'll put a 3 there, or 4-dimensional, 5-dimensional, or n-dimensional space right up there. Well, what are subsets or significant subspaces? Oh, we call this a space, Euclidean space, or Euclidean 2 space. What are some interesting or subspaces that need to be pointed out? One is the whole space itself. Any space is a subspace of itself. That's really by definition. Any set is a subset of itself. If we want to refer to things that are not the original set, we usually say it's a proper subset. But we don't need to get bogged down in terminology. I don't know how many of you have seen symbols that look like this versus this. This would mean that A is a subset which could include B of B, and this means A is a proper subset of B, so A would not include everything in B. If you've seen that before, good. If not, well, now you've seen it, but I'll mention it when I use it again. But in terms of this course, the interesting subspaces of R2 are straight lines and points. And what is a straight line? A straight line really is R1. The regular real number line is just embedded in 2-dimensional space. What is this? This is R0. I don't think people normally write it that way, but that would just be a single point. That would be a 0-dimensional space, which is just a point. Not very interesting. Now you can immediately surmise or imagine what will happen if we bump this up to 3 dimensions. If we bump this up to 3 dimensions, we write it like this, R3. It's Euclidean 3 space. Oh, Euclidean means because the geometry is the standard Euclidean geometry. I think I did mention in class, I can't remember. But if you do, there are different kinds of geometry. For example, where the interior angles of a triangle do not necessarily add up to 180. Remind me in class, I've seen before, I'll show you. Simple examples. But if we want all the regular things to happen in Euclidean geometry, for example, parallel lines don't cross each other. Interior angles of any triangle add up to the sum of 2 right angles. If we want those things to happen, we say it's Euclidean space after Euclid, the great Greek geometer. Now, let's take a look at 3-dimensional space. Let me just get an entirely different. Oh, you know that final solution we had that I just erased? What we want is a graph so that we can enter that form of the solution into the grapher, and it'll produce a graph. What should the grapher want us to input? A particular solution, and then the free variables with the vectors, they multiply. Particular solution plus some vector times a free variable. We should be able to enter that. And I would think it would ask for, there'd be like a blank space or something, so you can input the particular solution and a blank space where you could input the vector and then the free variable. And then it would produce a graph. So in that last case, it would produce a graph of a plane, and we could take a look at it. Now, in the case of 3D, because this is difficult to draw. I'm not really going to try to draw it, but in the last case there, what did we have? We have the x-axis, y-axis, and the z-axis. Now, this way of drawing this is by convention. A lot of you have probably heard this right-hand rule. If I'm pointing out, the x is supposed to be coming out at you. And if I point my finger this way and I curl it around like this points in the z direction. So we call this a right-hand coordinate system. If I did my left hand and it's coming out at you, and I want to curl it so it goes towards the y-axis, well, then the thumb goes down and we make the z-axis go down, and that would be a left-hand coordinate system. We don't use a right-hand coordinate system because most people are right-handed. We use it because of some properties of how electricity and magnetism work, how the universe actually works. Remind me and I'll show you in class. It's actually not as arbitrary as you might think that we draw the XY coordinate system like this. Okay, nonetheless, remember in the 2-dimensional case, what we really had is we had a straight line in the case of homogeneous system. And then the original system was the same straight line, it was just translated or moved or pushed over somewhere. Well, what would we have in the 3-dimensional case? We would have a plane. And in the case of the homogeneous system, the plane would go through the origin. So we'd have some sort of a plane. And remember, this is, in general, we can think about how maybe try to draw these. It's not an easy thing. I'm trying to draw a plane and somehow so it looks like it's floating about this 3-dimensional coordinate system. That would be, if it went through the origin, that would be the homogeneous system. The original system would be the same plane, but translated, moved, shifted somewhere else. Where would it be moved? It would be moved, but it would maintain the same orientation in space. And eventually we're going to have to talk about what does that mean, same orientation in space. It's not even as clear how to measure the angle. When you have a straight line, like if you have a horizontal line and a straight line, I think it feels fairly clear what that angle is. But if someone asks you, what's the angle that this plane makes? You'd have to say, well, angle with what? And a plane isn't even a straight line. So what is even meant by that? So we'll have to talk about that. But for right now, we'll take the intuitive notion. We sort of know how this plane is in space. I'm looking around for a piece of paper. Unfortunately, I don't have one. But here's a plane in space. And we can sort of do this with it. But you get the feeling that we're not changing the orientation of the plane. And where would it shift to? It would shift so that the plane goes through the particular solution. And I don't remember what it was, but let's just say the particular solution corresponded to this point right here. We can also think of it as a vector. It would mean take this plane and put it so that it went on that point. And that's a general property. So the homogeneous system really tells us what the space is. Hey, now what are the subspaces of R3? Well, planes, lines, and points. This shouldn't come as a big shock. So when it comes to R3, three-dimensional space, the proper subspaces are either a two-dimensional plane, a one-dimensional line, or a zero-dimensional point. Now this is linear algebra, and we're going to see that in the land of linear algebra. There's lots of other spaces, curved spaces. Sphere would be a curved two-dimensional space. A horse's saddle would be a two-dimensional curved space. A parabola would be a one-dimensional subspace. We're not going to be dealing with those. We're just going to be dealing with planes, lines, and points. Now, bump this up to 4 dimensions, which I can't draw. Sorry. If you know anybody who can, put me in touch with them, because I've never heard of anyone who knows how to draw R4. There's various ways we can sort of like trickster ways of trying to draw it. Like we do something like this. We say, suppose that, although that looks like a plane, but just suppose has 3 dimensions. And we may say, well, there's a new dimension, say t, coming off it. But really, I'm just trying to, in some way, symbolically represent it. I haven't really drawn a representation of it, not so that I can see what it looks like. But what do you think the proper subspaces of R4 are? And yeah, a 3-dimensional subspace, which is flat in the same way a plane is flat inside of R3. And a 2-dimensional subspace, so you can have a plane in R4. 1-dimensional subspace, you can have a line in R4. And a point, you can have a zero-dimensional subspace in R4. And we can keep on bumping this up. I mean, we're going to be able to do math where we might be talking about 8-dimensional Euclidean space, and maybe we're curious about a 5-dimensional subspace of 8-dimensional space. And we could do a variety of things. One thing is we could go and pretend that we're seeing it. I'm not seeing that. I have some kind of vague, fuzzy way of seeing this, but I know it's not really the real thing. Okay, so that's enough for this video. And the point of this whole thing was the book is asking you to solve the system and to solve the associated homogeneous system. And I'm pointing out the relationship between the two of them. I'm going to end this video, post it, come back, and I'm going to do this problem, 3.21 on page 34.